very warm welcome to our online International Women's Day event. It's fantastic to see you join us today, and we are truly excited to celebrate the incredible achievement of women and to look forward to a future where all individuals can thrive. So, today is a day for celebrating International Women's Day, and it's happening at a truly significant time. Artificial intelligence is rapidly reshaping our society, and the contributions of women are not just important, they are revolutionary. As we embrace our theme, redefine possible, let's remember that at this critical moment, as AI reshapes society, women are not just participating, they are revolutionizing the future of technology. So let's challenge the status quo, break barriers, and take bold action to create an inclusive, transformative future. Together, we can redefine what's possible. This powerful statement perfectly captures the essence of why we are here today. So, now, it's my absolute pleasure to introduce our first speaker for today's session, Amel Sellami. And Amel will be talking us on a fascinating journey into the world of diffusion models, specifically focusing on building your own stable diffusion. So, please join me in giving a warm virtual welcome to Amel Selami. So, you're welcome.
Thank you. Thank you very much for this introduction, Anna. Hi everyone. Today we will be talking about, like as Anna said, like diffusion models, building your own stable diffusion in this International Women's Day. And basically, like what I want to start is that, okay, I think it's missing, but it's fine. So basically, my name is Amel. I've been working at InstaDeep since the last 6 years now. I'm also like a machine learning engineer and a team lead at InstaDeep, and also I am a Google developer expert in machine learning and a mentor at the Google for Startup Accelerator in the MENA region. Today we will be more or less focusing more on like the stable diffusion, how you can build your diffusion model. We will try to go through the different parts of how the diffusion works and all of them, trying to understand the math behind it. And for that, like basically, please let me like share my screen again for like sharing the Jupyter that we will be like seeing and using to build like our own stable diffusion. So basically, just a quick overview. And this was like introduced in the Learning in Daba 2024, and it was like basically the authors were Sebastian Bernstein from Google DeepMind, Kevin and myself from InstaDeep, and we created this kind of basically like diffusion practical, and we will go through it today. And it is basically intermediate to advanced for some knowledge, and we will talk about like the different things related to diffusion models. And like I will share lately the different parts of the practical, or let's say like the introduction to this diffusion models. But basically what we try to do is that we have like denoising diffusion models are variant of generative models. Everyone basically knows that, and it serves as a backbone in the recent advances in like basically image synthesis, including, for example, Dall, stable diffusion, Midjourney, and different kind of other models. So like basically these models, they use something called denoising process during the generation to produce high quality images. And in this practical, what we will try to understand are the fundamentals of the diffusion model, so the intuition behind it, why it works, and how they work in practice. We will cover all of these things. You can find all of this in the diffusion model space, or the practical from the deep learning in Daba community. So basically, what if the things that you should have, like it would be really great to have, is that familiarity with statistical methods, and basically familiarity, of course, with Python, NumPy, and JAX, because we will be doing this practical on JAX, basically. And the outline is that basically we have like the diffusion, building your own stable diffusion. We have like some installation, imports, some history, application. Basically, so an introduction to image generation with diffusion, like sampling distribution to generate images, like basically like uh, uh, a diffusion practical stable diffusion example. We will outline this section, but unfortunately, because it takes lots of like RAM and GPU, it's not possible for me to run it on the GPU for this section. But we will continue like basically understanding what are the denoising diffusion models, some math refresher about this, the requirements for diffusion, the noise scheduler of a diffusion. There's different kind of math refresher. I will try to go as much as I can on some of them, but not all of them. But you can have like more information in this prac that you can find online, and you can like deep dive later on onto the maths behind like the diffusion, and basically the forward process for the diffusion example, and then the reverse diffusion process, and then basically augmenting and reversing the process of a model, sampling, generation, image, and basically trying to put everything together from training, generation, and sampling. Yeah, there would be another section which is diffusion in one dimension, because as we will explain later, we can do it in not just in two dimensions for images. But I'm not sure if I'll be able to cover this up, because it will be very long, like kind of yeah, uh, like some like explanation. Okay, so basically, yeah, first things that we will start is by like basically importing the different kind of requirements that we need, and basically using JAX, GKMD, and Matplotlib, basically basic kind of packages for machine that we will be using, and of course we will be using JAX, and then some kind of like helper function that we will be using later on, of course. Okay, so basically, let's get started. Like diffusion models, some kind of a small history. Basically, diffusion models are generate data, and the idea is that we generate data by iteratively adding and reversing the noise. So basically, the whole idea behind the diffusion models is that you add noise and you try to remove that noise from the image, for example, that you have. And basically the process of it's like diffusion is based on the process of particles spreading out. So it's like particles trying to spread out, and it's kind of like in fluids diffusion models, they gradually distribute information, and it's the same kind of process. So diffusion has been explored basically as an alternative to GANs or variational autoencoders, and the diffusion models have evolved from their traditional roots in image processing, where they primarily employed for tasks like, for example, noise reduction, image distortion, or anything of sort. So basically, even right now, for example, at SADIP, we can use, for example, like diffusion kind of models on some types of text. And the type of text can be, for example, proteins, or like any kind of antibody kind of realm. So basically, it's not only for images, but we can use it also for text, for proteins, for different kind of text, and like there are huge like different kind of models that we can do using that. So basically, the early method of handcrafted mathematical models to describe the diffusion model uh, is like the advent of like deep learning. It marked a transformative shift in this sense. By using neural networks, the diffusion models can now learn the diffusion process directly from the data, and this will help in unlocking like the potential of different kind of applications. And as I said, it's basically not just for images, but for example, some kind of application, we can use image synthesis, restoration, generation of context. It's also used for sound, or text, or any kind of video, for example, or even drug discovery. For example, at Institute, this is something what we do in collaboration with our mother company. For example, in bioinformatics, it can be utilized to a vast space of molecular structures like protein, antibodies, or any kind of like thing, molecular for potential therapeutic use. And for example, it can be used for anomaly detection or anything of sorts. Okay, so basically that's a quick like history and quick introduction of like the of diffusion models. So let's start with the first things first. So basically, how we're starting with the introduction to image generation with diffusion, and basically we'll try to sample distribution to generate images. Like basically, images can be like seen as a distribution of the data of pixels that we have. Like each image have pixels randomly from 0 to 2020 to 255, right? Each pixel have a number. And what we try to do is like we try to sample a number from these kind of like distribution of the numbers between 0 and 255 to sample the image. The image can have a meaning. For example, it can be an image of a cat, it can be an image of a dog, it can be an image of a flower, or it can be a complete gibberish like kind of image. And this is what we're actually going to see. So basically, digital images like are in computers are defined by three kind of color channels: red, green, and blue, which is the RGB. And these primarily colors used to represent images in digital format. So to each pixel, it has like these three values: red, green, and blue channels. And by combining these three different intensities of these three colors, a wide spectrum of colors can be like created. And this is and the color intensity will range from 0 to 1, and 1 being most intense and 0 being the least intense. So basically, if we want to generate like images through sampling, we typically means that we want to sample these three RGB colors, right? And for each pixel in a smart way that results in an image as I explained. So basically what we have, like example, like here we have like different kind of color distribution. From the red mean, reds, the standard deviation; for the green, the same thing, and for the blues, it's the same thing. And then basically we'll try to plot something like this. And basically this is the distribution of the like basically the color intensity that we have from the green, the red, and the blue, right? The RGB colors that we have. So basically what we'll try to do next is that we try to plot samples from the distribution above. And to do that, like we can basically just run the code above, and basically just trying to randomly pick the red mean, green mean, and blue mean, using np.random, using a normal distribution in this case. As you can see, we use a normal distributions, and we will explain why later. We use generally Gaussian distribution and normal distributions for math behind the diffusion models. And then basically we get something similar to this. And if we want to sample from these kind of like pixels that we get randomly, we get something like this kind of image. And this kind of an image is kind of gibberish. It does not mean anything. But basically what we want to do in the diffusion model is that if we analyze something similar to this, which is gibberish, we want to go from something gibberish to something which mainly using like having a meaning, which is basically a cat, a dog, or it can be kind of image that we want to the model to understand or to learn. Okay, so basically if we want to go uh you can like more information about the different kind of things. For example, in here, like how would we even in like such a different distribution for the images that we want. And like basically a naive approach would be a simple linear neural network to predict the mean and the variance of the Gaussian distribution for each pixel that right. But this quickly converges on predicting the mean and the variance of the entire dataset. While the rough shape might be there, it will likely be blurry or hard to make out. So basically, the idea is that if we want to try to sample from this, we sample like in this process, the distribution, like basically to predict the mean and the variance of the Gaussian distribution that we were going to use, it's going to be blurry at the end of the day, or not very let's say generable, because basically if for example the shape of the cat changes, or like the place of the cat changes, it will be very hard to the model to have a very generalistic point of view of these kind of type images by just explaining on having one Gaussian distribution across the whole different kind of pixels of the image that we have. So basically, this is where the Gaussian, like the generative models comes into play. And then we need to define a way of sampling the pixels that is dependent on the other pixels in the image. And this is how the diffusions offers an intuitive way of how we do this. So basically, as I said, this is the section that I won't be able to like use, but you can try it yourself. And basically what we're trying to do is that we're trying to use the diffusers from Hugging Face to and like basically install everything, and then basically create, for example, an image of a Senegalese grand sunrise with a fisherman. Like basically, if you're going to use the stable diffusion, you'll be able to like to generate something like this. We will understand why it works and how this works, but this is basically just trying to, if you have like enough RAM or enough GPU in your like computer, you'll be able to run something similar. And basically, this is just a proof of concept of that you can use the stable diffusion into your like like models directly to generate the type of images that you want. But basically, yeah, okay. So what are like, if like, unfortunately we were not able to see like the importance of the diffusion models, but I'm sure everyone here have tried like Dall-E or something similar. But basically, what are the diffusion denoising diffusion models? Please let me know if you have any kind of question that we're going to tackle later on. Basically, like denoising diffusion models, commonly referred as diffusion, is a variant of generative models. I hope everyone is like familiar with some of generative models that exist, like GANs and stuff like that. And basically, the goal of a generative is to create a new instance of something after being given like many more examples of the same like kind of image, for example, that we have. And this kind of practical, I'll be only talking about image basically, but as we said, it can be applied to text or anything similar. So basically, uh, what we want to do is that we want to these models to generalize. For example, if you have an image of a dog or a cat, it can be generalized to any kind of image of a cat or a dog with different poses, different shapes, different kind of like places that exist in, for example, in the image. So basically, if we have, for example, like basically the idea, if we want these models to generalize, for example, if you have two separate images, for example, of a lion and an astronaut, can I create a novel image containing both? Or if seen a painting, for example, Van Gogh, could I like make a new image of a boa tree in the same style? So diffusion is the process of iteratively denoising or refining the samples trying from a random noise. The random noise that we created at this the start of this like notebook. And is it possible to have a process that denoises or refines or remove this kind of noise from this random noise from the image to create something that is meaningful? And like from this point, yeah, we will be using like diffusion for clarity. So basically, like if we want uh like like a diffusion probabilistic model, which is called a diffusion model, is a parameterized Markov chain trained using variational inference to produce samples matching the data after finite time. So basically, that's the whole. Let's say that's the idea behind diffusion models. Why is it a Markov chain? It's a Markov chain because basically it only depends on the time step t, and it depends on the prior knowledge that it needs from like the previous time step. And this is we will get into this conclusion at this later stage in this practical. So basically, what we know or what we have is that the diffusion model is a Markov chain, as I said, because it depends only on the time step t, and it does not depend on the prior knowledge that it gets from each time step before. And it uses variational inference to produce samples matching the data after finite time. So basically, it's not like training any deep learning kind of model normally, but basically it tries to use the variational inference, or basically try to like capture the distribution of the data that we have from while training using variational inference. Okay, so basically in the diffusion process, we have two like kind of like processes: the forward process and the backwards or the reverse diffusion process. So the forward process is the process of adding noise to an image, And generally in practice we use only the reverse diffusion or the backward process. But this is the math, our how why it works. To make things why it works, we need to introduce the forward and the backward process of the diffusion. And the process of adding noise to an image is like basically we can define it as a distribution, which is basically a q of x t, like this t, and define like the where xt is basically the noisier version of the image before, like xt minus 1. And the reverse process is that it removes the noise from an image by moving forward to some references. And we can define this as a distribution of the, like basically the q of xt minus 1, where x, knowing the ground truth of the image, and xt minus 1 has less noise than xt and is closer to the target x0. So basically what we try to do is that xt minus 1 knowing xt and x0. And this is basically we try to remove the noise from the diffusion process. If we try to visualize it, it's something similar to this. Sorry. And basically, this is the whole idea. So basically, you have an x0. The forward process is that you go from one, like from xt minus 1 to xt plus 1, and the reverse is like this, the reverse of it. So basically, xt plus 1 to get to xt is basically xt knowing xt plus 1 and knowing the ground truth that we have, which is x0. Same for xt minus 1 and xt. If we try to see it as an image, is basically something like this. This is our ground truth, our image of baba tree, for example. And then the forward is that we added some kind of noise into the image, which is xt. And the final is that we have a very blurry image at the end, or we can call it gibberish, we can call it noise, or we can call it whatever we want. And the backward is that we want to go from xt to x0, passing by xt alternatively in some ways. And yeah, basically, yeah, for example, like x0 is the ground truth, the xt is an image noise by t steps, and t is the maximum number of noises. And t is a hyperparameter, by the way. This practical, we will have it like at 300. So basically, what is xt knowing xt minus 1? So basically, this is the like the random variable of the distribution. And basically what we try to do is that the xt knowing xt minus 1, this is the meaning behind the qt in this kind of words. And basically what we're trying to do is that yeah, that's basically what we are trying to understand. So basically the intuition behind the models is not limited to image. It can be applied to other domains, as we explained. And we must be able to undo the forward noising process. Given a target x0, you must be able to reverse the noise process and eventually reconstruct x0. And basically, yeah, and times the step, the data should be a random noise, as we explained. Okay, so basically there is another important thing in the diffusion process, which is diffusion noise scheduler. So basically, before moving on to defining the forward and backward process, we first need to find a noise scheduler. And basically, it's like a scheduler that will include noise at each time step. And we want to add or remove a small amount of noise with the diffusion function, while a later steps we want to add significantly. So basically, it's like the immobility tree. So basically, at the ground truth, we have no noise. Iteratively, after t times half, at each time we increase the amount of noise that we include in the image, and that's the noise scheduler that we are going to use. So basically, we define a noise scheduler, which is alpha t, as a decreasing scalar for each time step, ranging from example from 1 to 0. We also define a beta, and we also either would use either a linear or cosine decay. So basically, for like this is kind of math notation for this diffusion, but basically we will use the alpha and the beta to have the schedulers for our like diffusion process. Okay, so basically, if for example we try to like implement the linear decay for alpha, we're using JAX no pi. We will be using the jnp.lane space. It's the same thing as the np.lane space, but it's implemented for JAX. Unfortunately, I don't think we would have time to wait until you have like to check the code. Basically, what we try to do is that like we try to have a linear alpha scheduler, for example the alpha start and the alpha end start, alpha end, and then we create a gnp dot linspace using the alpha start, the end, our end, like basically, and the timestamp that we want to create this noise scheduler that we need. Basically just like a very clear let's say way of like choosing the alpha. Then we can choose this hyperparameter, like t equals 200 or 300. And then we have like, for example, the alphas and create the betas based on the formulation that we have above. And we like define like some kind of like math notation that we will be needing later. So basically, if we try to check like the plot beta schedule, for example, we would see like the alpha and the beta are like different. Like for example, this is the beta and this is the alpha. The alpha and the beta is like beta is 1 minus alpha, so it makes to have like this kind of like schedule in this kind of sense. Okay, so basically, as we said, we will be using the Gaussian or the normal distribution. And if we want to like learn more or remember more, Gaussian distribution which is basically the common distribution for modeling the continuous random variables. And basically, this is the formulation. Everybody knows like the math behind like the Gaussian distribution that we have, and where mu and sigma are the mean and standard deviation, and because we can call them also the location and the square root of the variance, respectively. So basically, this is the formulation behind like basically the Gaussian distribution. So okay, let's take a more closer look on how the forward diffusion works. Okay, so basically we introduced the forward process. We want to define the process of iteratively corrupting or noising the image. And for that, we define the distribution, which is Q xt knowing xt minus 1, right? And this is what we talked about at other earlier step. So why we use, we can define this forward noising distribution as a Gaussian parameterized distribution, but why do we use the Gaussian distribution? So basically, it kind of have like difficult some kind of mathematical foundation behind using the Gaussian. And for example, one of them is that basically you have the central limit theorem, and that it sums like basically if you have like some independent random voice, it tends to follow a normal Gaussian distribution. It makes like the property of using Gaussian noise a natural choice for modeling random perturbations in this case. This is one of the examples, but you can see that we have like it can be because the Gaussian distribution are also well understood and very have closed form expression for probability density functions. And yeah, basically for the noise, the forward noising distribution is defined as xt knowing xt minus 1. And that's the formulation. So basically where the mean or it's basically alpha t, the alpha t that we defined earlier, xt minus 1, which is the mean, and sigma is 1 minus alpha, sorry, is the variance. We can also sample xt from the distribution that we have directly given x. So if you're more interested into knowing more the derivation, you can check this kind of like math behind it. And basically, this is the formulation that we will be using to define the forward process. So alpha bar, which is basically the product of the different alpha t, and this will be useful during training, as it will be more efficient to directly sample xt given x0. So basically, if we want to, I will go directly to it. Basically, how to sample from the like implement forward diffusion. It's basically something similar to this. So basically, what we try to do is that we sample noise Gaussian random normal, as we said, with the mean 0 and variance 1, and then basically we make sure that alpha is in the correct shape, and then basically we sample the Q sample, knowing the start, the T, and the noise that we're going to add. So basically, it's that these are like we're trying to do these kind of like the math formula to put it into code, as you can see in here. Okay, so basically, yeah, I think I will try to go like not much, but into the details of the math. But it's basically it uses the expectation and why it makes sense at a later stage. Okay, so yeah. So basically, as we know, the expectation this is for a discrete variable or for continuous variable. We can use like the integral or the summation depending on the type of like variables that we have. This is expectation. I'm sure everyone is familiar here with it. And basically basically what we try to do for the math diffusion is that we can think of the data as we observe as a represented or generated by associated unseen latent variables, which we can denote by the random variable, for example, z. So the objects we encounter in the actual world may be generated as a function of some higher level representation. What we observe can be interpreted as a three-dimensional projection, and we can approximate latent representation that describe the data we observe. So basically, in general, we seek to learn the lower dimension latent representation rather than the higher dimension ones. This is because we try to learn basically if you try to understand the higher dimensions, it generally is fruitless or it like a fruitless endeavor without strong priors. So learning lower dimensional latents can also be seen as a form of compression and can potentially uncover some semantically meaningful structures describing observations. So basically what we try to do is that we try to approximate a latent representation that describe the data that we observe or that we have in our data set. And that basically what we're going to do is that the evidence lower bound. And basically in math, we can imagine the latent variables and the data we observe as modeled by a joint distribution, for example, P of x knowing z, P of x and z, right? And one approach to generate models is termed like learner model to maximize the likelihood P of x of all the observed x's that we have. And we need the likelihood P of x, right? And how we would recover this from the joint distribution P of x and z. So basically, because we have like this joint distribution of the latent data that we observe, z and x, and because we don't know like this kind of distribution, what we're trying to do is that we try to recover or to learn the maximum likelihood P of x of all the observed data that we have or all x's that we have. And to do something like this, if we're going to talk about, for example, something which is integrate out the latent variables z, which is basically using this kind of formula. Or we can apply the chain. So basically, these are the two methods to get the P of x, right? So basically, if we want to get the P of x knowing z, P of x and z, sorry, we can get the chain of rule. So basically, so because it's very hard to integrate this kind of like formula, because it can be very computationally not like viable or very hard to integrate out. One thing is that we integrating out all the variables that can be tractable for complex like models. As I said, it can also mean that we need to, the ground truth latent encoder POZ knowing x. So what we're trying to do is that we will return from both equations named the evidence lower bound or the elbow, which is a lower bound for the evidence, and it's quantified in this as the log likelihood of the observed. So basically, the log likelihood is used for several reasons: preventing underflow, relation to information theory, or convexity. So the elbow is defined as something like this. So basically, it's the expectation of the q z knowing x of the log log of p of and z divided by z knowing x. So the relationship is that we will try to go until we find like a minimum, let's say, for the log of the p of x that we need later on to define the formula. And basically what we're trying to get into this kind of formula using the ALPO methods. So basically, if we try, but basically, how do we get this kind of equation? For example, we have the p of x that we were trying to, we apply the log to it, which is basically the log of the x z of z, right? And this is what we said, like integrating out this kind of like formula can be very. This is why we apply the log to it, and basically what we try that we include the distribution of z knowing x for like in the numerator and the denominator, and which is basically, if we try to look at it, which is basically the kind of expectation, the formula of expectation, log of formula of expectation, and then basically to go from here to this, it's basically applying the just an equation to get from to basically integrate or including the log inside the formula, the expectation that we have. So yeah, so basically this is how we get from the p of x to till um, till what we need. But this formulation does not actually give a proof of no intuition exactly why the elbow is actually a lower bound of the evidence that we have, right? Why is it a lower bound? So basically, if we try to like get the information, is that basically what we try to do is that log b of x is this way, multiplying by 1, which is basically 1, this, and then get into until it's basically we have this, and then the Kyle divergence. And basically we always know at the end of the day that the Kyle divergence is always bigger than or equal to 1, so we get this in kind of inequality. And this is like more of an information how it works and why is it so why it works. So basically this explains the math behind it. But if we try to go and why we are going to use the elbow in variational inference, because elbow is a fundamental concept in the variational inference, and as we said, the diffusion models use variational inference to train and involve the latent variable and inferring information about them. So basically this is why we use the elbow. I'm going to try to skip some certain like maths in here, because it's going to be very math heavy otherwise, and we need to go to the reverse process also. So basically that's the forward process. Like I try to get like small information about like why it works, but of course it needs more like if you would have like time for a pen of paper to just like try to understand how it works. But this is just the general overview. As we said, have the probability distribution, we include some like it's a Gaussian process, and what we're trying to do is that we try to make it into that like using the elbow and this forward process to make like the evidence why it's working in a way or in another. Okay, so basically in an example of a forward step, for example, if we have like this kind of image, what we're trying to do is that we apply the normalize from minus 1 to 1. Why do we normalize the image from minus 1 to 1? Is that basically if it's going to be only normalization between 0 or and 255, for example, is going to like include later on in the training some stage of like vanishing gradients or exploding gradients because it's big numbers. Or if it's between 0 and 1, it's not very like it's not it not can't and take into consideration the negative like distributions with like the negative minus 1, for example, in this case. This is why it's between minus 1 and 1. This is why we try to include this to normalize this between minus 1 and 1. And basically the as we can see, we have like some kind of images, and what we try to do is that at t equals to 100 we have like some kind of noisy images. And yeah, so basically like how do we do everything, why it does make sense, why so basically like we explain the math behind the elbow, and by introducing the latent variable, our objective becomes capturing the underlying latent structure that explains our observed data, and that's our goal. So in essence, we aim to align our estimate posteriorly with the true posteriority that we have, minimizing their child diversions. So, however, directly optimizing these diversions is computationally infeasible due to the inaccessibility of the true posteriority that we all know. So, interestingly, the elbow and the child diversions are linked. Maximizing the elbow is equivalent to minimizing the child diversions in this case. And this is like basically how do we do this is basically VIEs or variational autoencoders and diffusion models use variational inference. And basically what we try to do is that we directly maximizing the elbow. This approach, the variational, because we optimize the best amongst the family of the potential posterior distribution parameterized by phi, it's called an autoencoder because it remains of the traditional autoencoder model where input data is trained to predict itself after undergoing an intermediate bottlenecking representation step. So basically, like we will try to, this is the posterior matching term. Like if we apply the chain of rule as we got from here, the chain of probability, and then we split the expectations, we get the reconstruction term and the prior matching term, which is the definition of the Kyle divergence. So, yeah. And if we, like, basically the idea is that if we get, uh, like, the elbow as like, so basically the lower bound of the marginal likelihood of all the observed data, and it serves as the objective function for training the VIU by maximizing the elbow. So basically, after like doing some math, we understand that like maximizing like the elbow is like minimizing the child diversion that we need at the end of the day, because child diversion is like basically we try to, because we have the distribution of the true data, which is our distribution, and this like the model that is going to train to generate the distribution, and finding the minimum between these two is like basically saying that maximizing the elbow. And because we know the elbow, it's easier in this way to train this model by maximizing the elbow compared, because sometimes it's very hard to find like to integrate out all the marginal or the posterior distribution that we have. So the encoder in the VIO typically models the latent space as a multivariable Gaussian distribution. It means that the encoder outputs the parameter Gaussian distribution for each input data. By doing so, the VIO can capture complex relationship between the latent variables and generate diverse outputs. And like just like in summary, the VIO strength lies in the ability to jointly optimize both the encoder and decoder through the maximizing the elbow, and the use of multivariate Gaussian distribution for the encoder allows for a flexible representation of the latent space. If we can get into a conclusion or a summary, that will be the summary for the forward process. Okay, I think I don't have like much time. I'm not sure if like anyone have like okay. So basically, let me go through the reverse process very quickly also. And basically, now that we have like the forward process down, this is the formula behind the backward process. And this is actually like the essence of the diffusion model that we will get into hopefully in a minute. So basically, we can define this reverse denoising distribution as the Gaussian parameterized. We will not get into how we can achieve something like this, the math behind it, because it can be very, very tricky, but this is the intuition behind it. And it's basically, we have like here, we have the mean and we have the variance behind our let's say reverse process. Okay, yeah. I think I'm going to skip the math behind this section, unfortunately, because it's going to take a lot of time to explain it, but you can like check it if you're interested to know more why it works and how it works, and basically the expectations behind how we get into something this at the end of the day, starting from like basically q of t minus 1 knowing xt and x0. Like basically, if you're interested in how it works, like you can find like the math behind it in here. And basically, what we're trying to do is that we will try to get the reverse like diffusion practical. So basically, we get like the giant formula that we have into some kind of code, as you can see. And then basically, what we're trying to do is that we help like to digest these kind of equations. We try to visualize the distribution. We'll consider, for example, in this example, a single scalar value where x0 equals 0 0.5 and xt equals 0 1. And then we try to see the distribution of the xt, as you can see. It's like basically normal Gaussian distribution depending on the t that you're going to do. And then augmenting the reverse process. So basically, we how we go both from the forward and the reverse of a problem. The reverse process is conditioned on x0, right? And what will x0 be in practice if you generate novel images, for example? This is where the model comes in. We let the model make a prediction of x0 referred to as x0 hat, and then use the reverse process as normal. So basically, like the issue is that, as we said, if we want to generate this, the model won't be able to do something like this. So this is why we refer to we let the model make a prediction of x0 referred to as x0 hat, and then use this the reverse process as normal in this kind of example. Okay, and concretely what we're going to do is that we have like this, the like p of xt knowing xt, which is this kind of normal distribution that we have, and the model predicts the distribution over x hat, and alpha t is defined as earlier as in the section before. So basically, we introduce the x0 hat that we have, and what we're going to try to do instead is that we have the x0 hat knowing xt conditioned on the c, where c is a conditioning input and theta are the model parameters that we have. So basically, the model to represent a probability distribution using xt, the conditioning input, and theta parameters of the model that we have. So the models, diffusion models like the one used in the previous section, C represent an encoding of the text conditioning, for example, and most commonly, for example, for a frozen clear text encoder is used for this as text embedding R, which already trained to contain information relative leases. So basically, it's like if we want to ask, like, for example, clip or any kind of like show me an image of something like similar to boa tree or something like that, conditioning on this conditioner, which is C, the text image that we have, and the XT that we know, and the reverse process, it will be able to generate the new image that we want. Okay? Yeah. And if we can see, for example, in here, like if we will now visualize both the xt minus 1 and xt and q of xt minus 1 xt, knowing xt and x0 previously, we'll let xt be a scalar in this example, and we will let xt have two like dimensions. For example, we will, if we realize the distribution, it will be something similar to this. So basically, this is our xt, and this is the two, like, let's say, probability distributions, or let's say the variables, the random variables of x minus 1 knowing x0 and p of t minus 1 knowing xt, if we try to model them using the image like this. So basically, the shape of the distribution is shown by the red and blue circles, where the radius given on indicates the variance. Notice how when t decreases, the radius of the variance decreases, and the mean shifts clearly amongst the dashes line towards each respectively x0. When t equals 200, the variance is at its maximum. So basically, if we try to play around, and for example with t, I'm not sure if it's going to work or not. Like we can see like the, okay, yeah, sorry, I think I need to redo it again. But like basically the two distribution of the, like the blue and the rest try to get as possible to among themselves. Okay, so basically, if we try now, we have the forward process and we have the backward process. So basically, how we do the training and sampling, generating the images, like basically putting everything together. Like the training goes as follow. Okay, so if in each sample C, X, 0, and T is randomly sampled into Midjourney from 0 to T. So basically, you would say, like, I'll explain this in a minute, but basically we just pick a T. T is where after a noise of T time steps, we have T. So basically, let's say if our maximum noise is T equal to 100, for example, a sample can be 100, 15, 50, 30, 35, or something like that. This is a randomly sampled integer between 0 and T for each byte item. And we sample xt basically on the probability distribution of xt knowing x0. And the model predicts the x0 using the model that we have, and then we compute the loss and update the weights. Basically, if we try to see it, it's something like this. For example, if we have a frozen clip model, what we try to do, we added some noise. Like for example, this is when we have a noise of xt, let's say t equal 50. Okay, we add some noise, we include the diffusion, and then we have like the x0 had an xt distribution, and then we have the cal diversion loss that we calculate, knowing the true distribution of the data that we have. So basically, the cal diversions try to find the minimum between the two different distributions that we have: the distribution that the model generator, or the distribution of the diffusion model, and the distribution of the true ground truth that we have. And this is the example. But basically, we do this multiple times, and we do this like basically, if we try to show it, yeah, we explained this. So basically, what we try to do is that we generate and sample. So the process of generating novel images is relatively straightforward. We simply start with some random sample and iteratively decode until we reach x0. So we do this multiple times, not just one. We have like a frozen clip model. We include the xt. We generate the distribution until we find the x0. So basically, we do this over and over and over again. If we can get into a conclusion, so basically, this is quite different from how the model is trained. The time is from a random noise and iterate t from t to t0. Why does this work when this is how the model is trained? This is not how the model is trained. If the model has been sufficiently trained for long enough, it should have seen the same type of images for all the values of t. So it shouldn't be an issue. Once again, why it works? Because if you have like trained the model to from different kind of t steps, if we sample directly from a t step, it will be able to generate something similar, or to denoise the steps directly. So basically, yeah. I think I'm just running out of time, and basically, yeah, there's just the diffusion in one dimension. That basically it's just like training a model in one dimension. I will have time to explain all of this right now, but just wanted to like say, I hope it was clear in some sense. Like we understand like the forward and the backward process of the diffusion models, and basically just trying to get a hint of the intuition behind the math behind it. And basically, yeah, if you have any questions, I'm very pleased to answer any of them. Thank you very much for your attention.